It's impossible not to be emotional about flying, but what that emotion is can vary quite a bit. For some, it's the thrill, the wonderment of a human being airborne, hurtling through the skies at impossible speeds. For others, it's fear, the lack of control, unimaginable heights, bumps along the way, and the terrifying lack of legroom. It can be wonder, the feeling of exploration, the excitement of seeing somewhere new at the destination and along the way. And of course, joy, a journey back after too much time away, seeing old friends, embracing loved ones, returning home, or finding a new one.
There's no escaping the wonder of mechanized human flight, and proof of that is in the game we're about to talk about today. Microsoft Flight Simulator is one of the longest running game series of all time, and over its 40-year tenure, it's also been a showcase for the power of video games. Not just their power to simulate real-world places, but their power to stir emotions in players.
Microsoft Flight Simulator is among the most beautiful and technically impressive pieces of software ever made, a labor of love for two teams separated by an ocean and 5,000 miles, because that ocean and each of those miles are actually in the game. You see, Microsoft Flight Simulator contains the entire world, every country, every city, every airport, road, almost every tree. And in this video we're going to explore how the teams achieved that and more, how they created their digital twin of planet Earth, the way they breathed life, weather and nature into that world, how they modeled dozens of planes to a higher degree of fidelity that we've ever seen, and in many ways, most importantly, the effect of releasing a game that allowed people to visit home as a global health crisis has billions of us grounded.
I've been obsessed with the story of how this game was made for a while now, so it's my absolute pleasure to share with you. So please sit back, relax, and let us take you on one of the most unique journeys in game design you're ever likely to be on.
Alpha 3901 taxi. 3901, runway 4 right taxi, Tango Yankee, cross through right center left. Alright, 34 right Tango Yankee, cross the through southwest, 3901.
I've been at Microsoft for over 20 years now, and so the notion of making another flight simulator had been around ever since I joined the company. Actually, in 2000, there was obviously still some products going on, but we had stopped in 2007 with Flight Sim 10. It's a fascinating IP inside the company because it's our oldest IP. It's our oldest, longest running IP. It's always surprising people when they say it predates Office and Windows. It's a fascinating pride in the company for this particular product type because it goes all the way back to 1982. Whenever a version came out, it pushed what was possible on a PC at the time. And that was super important. It was always an evaluation. Do we have something new to say? Is there technology that really takes us forward?
Jörg Newman, a veteran of flight sim, would lead the project from here in Seattle with a team of just over a dozen people, mostly focused on licensing, publishing, and feeding in expertise from other Microsoft teams, including Bing Maps and Microsoft Cloud Computing Tech, Azure. We'll dive into those a little bit later. But to talk to the developers of the game, we have to take a long-haul flight from the Pacific Northwest all the way to Bordeaux in France, the home of veteran game developers Asobo, a studio with quite the diverse resume.
We have really a two-sided organization. One part is more on simulation. We worked on fuel. It was a bike, truck, car, quad racing game. It was a little bit more arcadey, even though the engine was very realistic, but all the settings were very action-oriented. It was already open world. And the other side of the company has been more specialized in Pixar titles and action-adventure games, character-based.
Asobo has grown slow and steady over the past 20 years, from the original 12 to 210 today, doing a lot of support work and contract work on larger titles. As Sebastian said, around 2/3 of the team work on more tech-focused games, their open-world racer Fuel being a good example, while the other third works on more action-adventure titles, everything from colourful kids games like Up to their more recent, darker hit, A Plague Tale: Innocence. In fact, Flight Simulator and A Plague Tale were being developed at the same time, and remarkably, they share the same engine. Asobo has been collaborating with Microsoft for around a dozen years, starting way back on the Xbox 360 with the motion game Kinect Rush, and more recently with Microsoft's augmented reality tech HoloLens. And in fact, it was a HoloLens collaboration that planted the seed of a new type of flight simulator.
And it was in 2015, we worked on a HoloLens project together. And the HoloLens project basically took a few pieces of Earth, like Rome and San Francisco and Machu Picchu. The whole point was that you basically teleport yourself to a place on Earth in the AR, with the AR device, and you could walk around. And I remember Machu Picchu looked just amazing. It felt totally real, even though I'd never been there. It's exactly what I imagined Machu Picchu to sound like, and to feel like, and to look like. And then the thought was, can we do this worldwide? And I think we tested it. The thing that was probably the greatest advancement since the last version, Flight Sim 10, was the cloud. And oftentimes we think of the cloud as sort of almost like storage or something like that. But it really, in our case, it's more than that. We're doing cloud compute, and we're doing cloud streaming. Now that Microsoft has established this Azure stack, basically data centers all across the world, you can get massive amounts of data to people with low latency. And that was the fundamental idea. Can we get the entire world stored? Yes, because we have Bing Maps that had the world already. Can we get it stored? Yep, Azure storage. Can we process it? Can we do things to that world? Yes, Azure has lots of machine learning tools, and there's Azure Compute that helps us with that. You can spin up however many VMs you need. And then can we stream it to the end consumer? The answer was also yes. So it had lined up the ambition and the vision that Flight Sim always had, which was a complete Earth, was now doable at a much higher level of fidelity because you didn't have to stick it on a disk.
Okay, let's back it up a little bit because a lot of complicated stuff was just talked about. The HoloLens project showed that creating an accurate 3D representation of a place was possible by pulling data from Bing Maps. The question was whether or not this was scalable to do the entire planet, and the barriers were threefold.
1. Could you store the entire globe? Well, yes, Bing Maps has aerial photography of the whole planet. That's technology that's pretty commonplace these days. But most of that data is flat photography with some terrain height mapping, and flying over that would just look like traversing a painting of the Earth, albeit a rather bumpy one. To make a realistic planet, you're going to have to fill that in with 3D detail, buildings, trees, roads, and more. Some larger cities have photogrammetry available. This is the process of capturing accurate 3D data of buildings, rather than just flat images. But while we have photogrammetry of some larger cities, we certainly don't have it for the entire world. The Eiffel Tower might be scanned, but your uncle's bungalow in Kansas probably isn't. Painting in this detail, home by home, road by road, and tree by tree, could take the studio years, perhaps even decades to complete. Which brings us to number 2. Do we have the cloud computing capabilities to have VMs or virtual machines chew through all of this map data and, through algorithms the team has programmed, paint accurate 3D objects onto the entire globe? The answer again was yes. And so we go to the third and final technological obstacle. Is it possible to stream this data to people's computers with low enough latency that they don't even notice? And the answer again was theoretically yes.
Why was streaming this data essential? Because the sheer amount of it was something we'd never before seen in a video game.
When you look at what we have in Bing, we have 2.5 petabytes of data that store basically aerial photography or satellite imagery, and then also height fields. And that's 1.7 million DVDs worth. So impossible to put that somehow in a box and sell it in a store. It cannot be done. But streaming, that is now a thing. And then this is sort of the first time that I've seen a game that really uses that entire stack that we are now enabled with for an experience. And I think that's why it feels like a real leap ahead in gaming, because there's never been a project that's like, hey, the entire planet and every house, 1.5 billion houses and 2 trillion trees in a product. And it's enabled by the cloud, and it's enabled by the Microsoft tech stack.
You could do AI in your local machine, but you can't process the planet on your local machine. You need 10,000 computers. That's why only something like Azure can do this. Yeah, the challenge I think was to how do we get from all this data to something which looks like the planet.
We try to be smart. So we started with an itty bitty tiny team. It was the first build that came in. That was the Seattle map and the Grand Canyon map. And we flew around with a little Cessna and it worked. And it already looked good, but it was just a very specific use case. But it gave us confidence, honestly, to build the team. And that was probably the first time I showed it to anybody, because it was just between the, four of us trying something. Because that was really what I nowadays call the static world. It's just buildings and trees. And there's lots more to do, right? There's the dynamic world, there's a living world, there's all these layers. At some point we established, hey, we want to land everywhere, and that was way beyond what we had with that first prototype. But yeah, I mean, we took it step by step and grew the team carefully.
Alright, now let's get to the fun stuff. The tech was there, but a statue is nothing without a sculptor, and this block of marble was particularly large. An entire world packed full of houses, trees, buildings, roads, hills, mountains, valleys, weather, and so much more. So to turn this world from a photograph into something that resembled the real world with all of its depth and detail, the team at Asobo, with the help of some external partners, would have to create technology to help them sculpt this world. Algorithms that chipped away at the marble, and new technologies that filled in the details.
In February we started, and you have to, if you know how photogrammetry works, it's basically 3D photographs taken at a specific time of day. So the Seattle map, imagine we had a pretty damn good Seattle map, but it had shadows baked in. There's some stuff that doesn't look so good. The Space Needle didn't look so good, because anything that has an overhang, these things are taken by an airplane, and it takes a photo every second, and then it constructs a 3D point cloud, right? That's how that works. Overhangs not so good. Trees look like you draped over like a sort of a blanket of green. It doesn't really look like a tree. So there were certainly some issues. And then there were some early experiments done on shadow removal, for example. That was a big thing. We looked at Bellevue, which is it has a bunch of skyscrapers nowadays, and there were these shadows cast on the street, and didn't look great. So we tried there were some experiments. Can we get rid of the shadows and do procedural textures in between? There's clouds and photographs, right, but from satellites. So cloud detection, cloud removal, that was a big deal, and then also color correction, because when the planes fly overhead, they fly in stripes, basically in strips, and you get the Earth, it's complete, but it has these color breaks all the time, and because it would taken a different time of day, sometimes even months later, right? So there were some of the earliest technical hurdles to jump through.
Once they'd figured out a strategy for color correcting the world and removing shadows from buildings and clouds, the next target was trees. Tree models from photogrammetry look ridiculous, so the team would have to build technology to populate forests and streets with realistic-looking trees. To do so by hand would take years, again, probably decades, so they would have to use machine learning to create a process that would accurately paint the entire globe.
You give the machine two pictures. One picture with a forest, and let's say there's a stadium in the middle where there's no trees, and then someone goes and paints all the forests in whatever, red, right? You paint it. And you give the machine two pictures, and the machine sort of learns, if you do that millions of times, the machine sort of learns to do the same thing, right? Later you give it just a picture of trees, and it's gonna paint in red, right? This is like a very simple way of understanding. And if you do it enough times, then you get a system which is good enough, and then you can just give it tree pictures, and then you feed it, the entire globe, right? And so that is billions and billions of pictures. It's not perfect. It's gonna work, it's gonna work in 90% of the planet, then all of a sudden, it doesn't work at all in Africa. And so we have to refine it. So this thing has been redone several times. The one you see currently is the 6th or 7th iteration, right? We tried colors, we tried shapes, we tried machine learning, all sorts of things. Usually it's a combination of techniques, which can only really work because the planet is so big. If you had one computer, it would take a lifetime to process the planet on one computer. You just can't.
Even with a stack of Azure virtual machines crunching the numbers, it takes around 3 days for them to paint the world with trees. This tech was refined to recognize different types of trees based on factors like color and geographical location. But machine learning can't be used for everything. For example, the technology used to populate grass is a client-side algorithm that looks at the Bing Maps data and renders grass depending on a number of conditions and filters. It doesn't always work, sometimes green roads kind of throw it off, but it was the smartest way to produce the desired effect, as billions upon billions of blades of grass would have been simply too much for the cloud. But one problem that did seem to be similar to tree generation was generating the millions of buildings scattered around the globe. And for this, the team reached outside of the studio for some expertise, a company called Black Shark, who collaborated with Asobo to build this technology. But it wasn't a one-size-fits-all solution.
We have some buildings where like in Seattle, like it's 3D scan, so there's already buildings. So there's obviously it's not just done, right? We need also, is there texture, is this glass? So there's all sorts of stuff. So that was already handled on our side. But that company, basically they can build buildings in 3D when you have nothing. I mean, most of the time what we have is a top-down picture. And so they look at the top-down picture and find the roof color, but not only the color. And so they train the computer, some AI, to recognize, is it a flat roof or is it like this roof, right? Or what kind of roof is this, right? And then it can basically say, after enough training, it can say, yeah, this is a hangar, this is a school or whatever. It can find the type of building just by looking at the roof. They combine that data with data from OpenStreetMap or other data. And in the end, they spit out a building, which is, I would say, as close as possible. The goal was to make it seamless because there's so many different data sources and some are high-res, low-res, 3D, and you want everything to look as much as possible the same in the end. It's hard to see the transition when you go from actual real scan photogrammetry, right, where it's the actual building, and then next to it there's there's a village which is not in 3D. So then that buildings get generated, and then it goes into a rendering engine, and the shading has to be exactly the same, and really make sure that you don't see any difference.
Photogrammetry and building detection did a lot of the heavy lifting when it came to creating an effective 3D representation of the entire globe, be it your hometown, a village in a part of the world you've never been to, or a popular tourist destination. The algorithm tooled and tweaked by the studio can effectively generate realistic approximations, but there are some structures that the game needed to make as accurate as possible. Firstly, there was airports, and astonishingly, Microsoft Flight Simulator lets you take off and land at every airport on the globe. Be it a dusty strip in the outback or a major metropolitan hub, there are over 37,000 places to leave or come home to. By using Bing Maps photography, the team hand-outlined airport perimeters, which informed specific rules for the building generation algorithm to follow, creating approximate versions of terminals, gates, and hangars. Then they would trace other elements such as the runways, parking spots, even down to the taxiways. 80 of the most popular and busy airports were given a more handcrafted feel with unique architecture and added detail, with 40 more of these being given the finest level of attention with near perfect representation in the game, though how many of these you have access to depends on which tier of the game you buy. Many points of interest such as famous landmarks and buildings were handcrafted too. Many of these were created by the studio and many more have been developed by the community post-launch and added to an in-game marketplace. A community of passionate designers who can more quickly react to the needs of the player base. So if airports and cities are the beating hearts of human existence on this planet, then we better pay attention to the arteries. OpenStreetMaps provided a level of broad data and local knowledge to help the team craft accurate streets, roads, highways, bridges. Vehicle traffic on those roads was handled by a similar tech from Flight Sim 10, but mass instancing was added to help CPU load whenever you flew over large parking lots, as the team noticed that the old code was trying to spawn tens of thousands of unique car models and dumping performance.
Just like world generation, the human life on this planet was also created using a variety of machine learning, algorithms, and hand-painted detail. But this world was orders of magnitude larger than any other game world we'd ever seen, so how do you test to make sure everything's in its right place? How do you check for accuracy? And when is accurate enough enough?
There's still some bugs. Like there's some roundabouts where we don't really quite know the orientation of the cars, so they end up going like, you know, like the teapots in Disneyland. I mean, they kind of don't rotate quite right, and there are some bridges that, frankly, like here in Seattle, our photogrammetry is a little bit older, like it's from a few years ago. So one of the bridges actually doesn't exist anymore because it was a sinking pontoon bridge and it's gone. So they built a bridge right next to it. But some of our data still has the cars driving on the old bridge. So it's, because fundamentally the world is a dynamic place, right? It's not like there's a single truth moment and that's the world, right? The world constantly changes. So our data will always be, it's mostly an approximation. It's vast majority of it is correct, but are there going to be some problems and errors? Sure. And then we get a new update and then it's going to get fixed. So it's more dynamic than a typical game would be.
At some point, the world is too big to test. The test team on Microsoft side was very smart. So they made a very smart grid of the planet, and then they had locations which were very representative of all the regions on the planet and all the different situations. And then you really reduce the amount of testing. You know that if it works in Seattle, it's going to work in Portland. Stuff like that. And then you always do a little bit of random fly around. I think that just flying around with a Cessna takes years and years and years to test the whole planet, so you can't do that. But if you have a smart test plan which tests all the different cases, and then plus a little bit of random, just checking if the test plan is valid, I would say you would catch 99.9% of all the issues. There's always going to be something, like you've seen the monolith in Australia. Something can always happen, but it's going to be very limited.
The monolith Sebastian is referring to is this, a 212-story building in Melbourne that really doesn't fit in with the surrounding architecture, and its creation is down to a typo. While pulling data from OpenStreetMaps, the sim generated a building from the data field containing the amount of stories the building had, and instead of 2, a user, Nathan Wright 120, had typed in 212. The team has since updated the game to filter out this sort of clearly incorrect data. Okay, so by now they've built the world. It has mountains and oceans, cities and airports. It even has your hometown in it. So what's next? Well, eventually we're going to talk about the planes, but before we do that, let's talk about the single most important facet of flying a plane, the most critical factor in every pilot's flight plan.
And Papa 203630 is Bravo, what's our clear?
2032 affirmative, target table.
Thank you.
The vision was that the world is dynamic. And for that, you need a dynamic weather system. So we looked for what is the best available weather data in the world. And we ran into this company in Switzerland called Media Blue. And they are pioneers in their field in that they have this vast array of weather forecasting material and data, historical data, and also current data. And we basically talked to them and hooked them up with a Sobo. And then it was really a integration of their data, how to do it smartly, and then also how to render it in a way that it was believable.
So it's almost like Bing data, right? It's just that Bing data for the planet is mostly static, so York says it's gonna get updated from time to time. And Media Blue is the same. You don't pull the whole planet, right? It's too big. You say, I think we're pulling a few hundred kilometers around the user, and you just call the server and say, hey, what's the weather? And it's gonna give you some sort of a voxel space, right? It's like little boxes. Little boxes for the wind, for the turbulence, for temperature, for clouds. If you don't have the data, well, you can put random clouds in there, but what is really crazy is that it's actually real data coming from the world and then going into that system.
The atmospheric simulation going on in Microsoft Flight Simulator is fantastically complex, taking into account air density, humidity, and even pollution when casting light and generating clouds. The sun, moon, stars, and cities all generate their own light as the wind blows the clouds that bounces it around. In fact, the wind even creates water turbulence, making the landing of seaplanes more challenging.
If you have the sun going down and there's a cloud at 200 miles away which is creating shadow, it's gonna shadow the whole world, right? And so you have to actually get that. If the whole world is shadowed, that means that the clouds above your head, they're shadowed. But these then cast less light onto the ground. So the ground is now darker because the cloud above you are darker. The difficulty is what is the best techniques for whatever, for mountain ambient lighting. So for example, if you go at Courchevel and you go down into the valley, you're gonna notice that the ambient light of the sky is hitting the fog differently. And if you don't do that specific calculation, the fog is too bright in the valley and it looks weird. And if you actually account for this, the fog all of a sudden is right, and it feels old. It feels like a real valley. And so this is all different systems for whether it's mountains, valleys, clouds, airports, planes, and all these things. So it's one global illumination system, but which has dozens of little different systems optimized for each situation.
The weather effects in Microsoft Flight Simulator are frequently breathtaking. By default, you fly in accurate data for your area, but you're also free to change the weather to whatever you want at any time. You don't even have to pause the game. Not only is this world a digital twin and the weather copied from real-world data, but the team licensed FlightAware to accurately represent real-time air traffic too. But for a game with all of this detail, we've yet to talk about the most detailed part of the experience.
From the get-go, we said we're making a sim for simmers, and I can tell you that simmers greatly care about every single detail. So I think our detail, if I have it right, 0.5 millimeters or something. It's super high res when we need it, and every single piece of text that is in a cockpit has to be exactly accurate because they know it and they will tell you if it's wrong. We opted to have relationships with every manufacturer, so we actually license all the planes, and that what that gets us is a deep collaboration with the manufacturers themselves. And then sometimes they give us a scan already, it's in the rare case, but they give us access to planes and also to the pilots. For the planes, we actually initially started modeling the cockpits. Nowadays, you actually scan the cockpits. So this is just an evolution also where how I think games are. Like if you look at Forza, they're doing very similar things, right? It is now possible to get this just exactly right. And specifically for a sim that is really so close to reality, I think it's critical to get to that level of detail. And even the wear on the textures, and there's a button that gets used a lot. It actually, you will see that it gets used a lot, so it's not all factory new.
Asobo's audio team spent months capturing the sound of flight, from ambient cabin noise to open windows, closed windows, to 3D audio recordings at multiple points around the plane. The vast majority of Asobo Studio took flight lessons as well, to try and understand how the plane feels and to get to grips with the litany of systems at work during flight. And according to Sebastian, older versions of the game were able to simulate many of the systems. PCs in 2006 were pretty good at electricity, hydraulics, and fuel mixture. But one area where Asobo added much more fidelity was the number of control points on the plane that interacted with the physics of flight. In the past, the plane was taken as a single object, and the effects of things like speed and air pressure were universal. But Asobo threw out that single box and added 1,000 surfaces.
And funny enough, actually, the single point system didn't go up to 1,000 in one step. Actually, there was one point, and then I added one on each side of the wing, say, oh, that's better. And then on the tail, and then one more here, and one more here, and I said, oh. And the idea is basically to capture more and more detail. So it's, let's say, with a single point system, you fly over a bump in the air. If the bump is on the right wing, you don't get it. You don't have any change. And if there's the point on the right wing, you're gonna get the bump. But if there's just one point, well, you don't really get the exact bump, you get something, right? If there's now 10 points, oh, you get a better bump, and maybe it's shaped like this or whatever. And so we just added more and more points until we ended up over 1,000, because it captures more of the little details. And also it's and so in normal flight, it's really only important for the wind and the turbulence. But when you start doing aerobatics or stalls or spins, that's where basically a stall is when both wings stop sort of flying, right? They just drop. But when you stall sometimes and you're not careful, you can get it so that only one wing stops flying and the other continues flying. And then you spin. And this thing basically, yeah, it means that one wing is flying and the other is not. And so you need to have 2 points at least, right? And then you find out, oh, but stall is not something which happens just at one time. You can look at the videos on the YouTube. Some people put strings on wings, and you see that stall starts often in the middle, and it propagates out to the wing, right? It's a continuous phenomenon. It's not on off. And so we say, oh, in order to capture this, I need hundreds of points to actually have a stall which comes from the middle and goes outside. And that's why step by step we just wanted to capture more and more of the reality.
Yeah, and it was user based, right? We listened so much to what consumers said in the blogs and on the forums. We read that literally every day for years, and a lot of people said, well, the stall is just not right. and the stall in Flight Sim 10 was a hard-coded, hard-coded event. You are now in stall, and it never felt right. And so that at some point Seb was like, "Look, I'm just gonna add more," and now it's a realistic stall, which is great.
One of the things I love the most about video games and the work we do at NoClip is that games are very technical things, but the ways in which we all talk about them, it tends to be about the way they made us feel. I know this has been complicated. There's been a lot of machine learning and algorithms and data points, but I just want to leave you with one more, and I think it might be my favorite. I asked Jorg what happened when they took the training wheels off the player. What happened when, for the first time, they were presented with that globe and they could pick anywhere in the world to fly to? Where did they go? What was the place that was the most popular? Was it New York or the Grand Canyon or the Bermuda Triangle? His answer surprised me, and it probably shouldn't have surprised me considering the year we've just had. But Jorg said that 70% of players flew to the same place. They flew home.
Like I remember, like when the coronavirus hit, like I remember trying, like I was supposed to go, like you just said, I was supposed to visit my family, and I couldn't because they live in Germany. I'm like, oh, so I actually flew there and called my parents, and I shared the weather. We just talked about the weather. It was the same time of day, same weather. It looked exactly right, and I basically called them up and said, hey, I'm as close to you as I can get. I think we see that replicate a lot. The stories that people tell us. I mean, there's lots of emails we get every day of people telling us stories like this, and I think it's been if it was even just a little bit helpful in these trying times, I think then it was unexpected in many ways, right? Nobody wants this, but I think it brings the world moved away from us a little, and I think it's a little bit closer inside the sim, so I think it's great to see it.